when we do our physics questions, and pretty much every physics teacher or professor that I know typically has the same ideas. We use certain types of triangles repeatedly. It doesn't mean we can't use other triangles, but it's pretty common for us to use one of three types of triangles. We call these special triangles. These are all ideas and concepts we get from a math class, but we use them in physics, of course. First one's going to be a 45-degree triangle. Some people will call this a 45, 45, 90 triangle. I really don't think that's necessary because I know that if one side is going to be 45 degrees, then therefore the two numbers have to add up to 90, which means the other side has to be 45 degrees. So personally, I think calling it a 45, 45, 90 triangle is too much of a mouthful. I just call it a 45-degree triangle. And the nice thing about a 45-degree triangle is that the size or the lengths of the two legs are equal. I'm going to use the letter x. So I have x and x, which means if I can find one, I find the other. I can do sines and cosines if I want to find that. And that's usually how I go about doing things. However, there is a number that we can remember. If we kind of went through and did a Pythagorean theorem for a proof, we would find that this side right here is equal to, this hypotenuse is equal to the square root of 2, which is a number that is bigger than the number 1, multiplied by the length of one of our sides. That means that if it's x times something that is bigger than 1, that means that my answer is going to be something greater than x. And so you can either use this root 2x relationship, or you can just simply do a sine or a cosine. Personally, I'm going to stick with sines and cosines. You can always double check your work doing both of those. So that's the 45-degree triangle. We don't see that one as much as some of the other ones because a lot of your physics teachers and a lot of your math teachers, they want you to actually solve for each side, not just solve for one and know that they're equal. So that's something to consider when you're going through and doing your work. Here's another very popular one, the 30-degree triangle. And again, some people call it a 30, 60, 90 triangle. That's fine. I don't think that's necessary because if I have 30 degrees here and these two interior angles here, these two angles in my triangle, they have to add up to 90. So if that's a 30, this one up here has to be a 60. So I just know that automatically. So again, calling it a 30, 60, 90 triangle, I don't think is necessary, but that's okay. The relationship here, again, I can always do sines and cosines, and that'll work every time. The relationship here is that if this right here is considered side x, then this right here is going to be considered side 2x. This right here across the bottom is going to be root 3, which is another number that is going to be bigger than the number 1, multiplied by x. So we're going to find that our leg right here that is across from the 30 is always going to be half the size of what I had for my hypotenuse. And so that's one reason we like that in physics, because it makes it real quick and real easy. This side right here, this root 3 over 2, again, personally, I never use a root 3 in my calculator for no other reason than I'm faster at typing in cosine or sine than I am typing in the square root button and then the number 3. Second, square root 3, there's 3 keystrokes, whereas sine and cosine, I can do a single keystroke and I get the same thing. So again, that is my own personal preference. You can use x, 2x, and root 3x if you want. I'm going to be using sines and cosines because that's what I do. This last one right here is extremely popular. It might be the one that's maybe the most challenging to use just because the angles are kind of estimates. This is called the 3, 4, 5 triangle. It's what we call it, the 3, 4, 5 triangle. It might be smarter to call it the 3x, 4x, 5x triangle, but no one calls it that. We call it a 3, 4, 5 triangle. The 3, 4, 5 references the lengths of the sides. So this side right here is 3x, this side right here is 4x, and this side right here is 5x. So obviously what I'm looking at here is not sides that have actual lengths of 3, 4, and 5 necessarily. They are in a ratio that relates them 3 to 4 to 5. What we find is that the angle for a 3, 4, 5 triangle is about 37 degrees. It is not perfect. It's not an exact 37 degrees. So if you decide to use sines and cosines, your number is going to be slightly more exact, and it's probably going to have a ton of decimals, as opposed to just having a number that's rounded off using the 3, 4, 5 triangle. And as you know from my class, I love rounding off, so I like having a 3, 4, 5 relationship. The complement to 37 degrees would be 53 degrees. So those would be the two numbers that you want to look for. So we've got 45 degrees, we got a 30-60 combo, or a 37-53 combo. Those are the three most popular ones. So for this one right here, this 3, 4, 5 triangle, students sometimes struggle with this one. Basically, figure out which part of the triangle you're looking at. Am I looking at the small leg, the large leg, or the hypotenuse? Once I know which part I'm looking at, I can assign it a value. I can assign it as a 3x or a 4x and a 5x. And what I can do, either in my head because I'm good at math, or I can write it out. I am going to figure out, okay, well, what is my x going to be? Once I know what my x is, I can apply the 3x and the 4x and the 5x. So that is my 3 examples of special triangles. I'm going to do a couple sample questions. If you want to follow along and watch the sample questions, here we go. I have a 45-degree triangle given with a value of 20 for the hypotenuse. So since we're typically using this with our two-dimensional projectiles, I'm going to use VOY and VX because those would be the letters that I would use. So I can look at this right here, and I know that each side should be the same size. So for this one right here, I know that the sine of my angle of 45 degrees is going to be the opposite side divided by the hypotenuse. So my VOY is going to equal 20 times the sine of 45 degrees. I can do the same thing for VX. And VX, I'm going to find, is going to be 20 times the cosine of 45 degrees. I thought I didn't have to do that, Mr. Lohr. Aren't they the same size? Yes, they are. But since these are just some notes that I'm making, I'm going to do it both ways just to double check. So I've got my calculator here in my hand, 20 times the sine of 45 degrees. Enter, and I get 14.14. You know me, I round up. 14. I do the same thing with cosine, and yes, I get the exact same answer. Cosine is the adjacent divided by the hypotenuse. And if these two sides are going to be the same, then that means that putting them into a ratio with 20 also is the same, which means my 45 degrees is going to be the same on each side, 45 and 45. If you want to do the old root 2 trick, that means that 20 is equal to the square root of 2 times x. So if I take my 20 divided by square root 2 equals, and sure enough, I get 14.14 again. So you can use any of those methods. You can use sine, cosine, or you can use the old root 2x, x, and x example. As I told you, I'm not a fan of the radicals of the roots. I like sines and cosines. Moving down, I have this one right here. So I can think of this as a 60 degree as well. So if I was given a 60 degree instead, I can just put the 30 on the other side. I know that, I guess I probably should have switched over to a different color before. I know this is x, this is 2x, and this is root 3x. So I can find my values by using sines, cosines, or by using these ratios. So I find that my VOY is right here. Looks like that's going to be a sine function. VOY is equal to my hypotenuse of 50 times the sine of 30 degrees. If you don't know this yet, you're going to recognize that sine 30 is 1/2 exactly. And so I get 25 meters per second. That makes sense because 25, double that and I get 50. Vx is going to be equal to 50 times the cosine of 30 degrees. And so doing that, 50 times cosine 30, and we get 43.3. I'm going to call that 43 meters per second. It just so happens that if I take the square root of 3 and I multiply that by 25, I get the same exact answer. It's not close, it's exact. And last, the 3, 4, 5 triangle. You're not going to be told that it's a 3, 4, 5 triangle. You're going to have to recognize that you got the 37 or that you have the 53-degree angle. That means that I have 3x across from the small angle, 4x across from the big angle, and 5x is my hypotenuse. So this means, since I know that I have a 3, 4, 5 relationship, I can do this in my head or I can write it out. Looks like x is 20. So the sides have the same ratio, 3, 4, 5. I just use the number 20. So 3 times 20 is 60. 4 times 20 is 80, because 5 times 20 is 100. So this right here would be my VOY. This would be my VX. And if you wanted to, you could always use sines and cosines. VOY is going to be the hypotenuse times the sine of 37 degrees. When I type that in, 100 times sine 37, I'm going to notice it's not perfect. 60.18. Obviously, I'm going to round that off to the number 60. So the 37 degrees and the 3, 4, 5 triangle, they aren't a perfect match, but they're darn close. And all physics teachers, every physics teacher that I've ever met and will continue to meet, treat a 37-degree triangle as a 3, 4, 5. I do not care what work you use, sines and cosines, 3, 4, 5 relationships, root 2, root 3 for the others. I don't care which what you use for your math, as long as I can follow along, and the Vx and the VOY are values that are accurate. If you have any questions, make sure you come in and see me. Otherwise, happy physicsing.